Let's do some example problems. Problem 1. What is the energy in joules of an electron in a hydrogen atom with n equals 3? So the equation we need is E equals negative k times z squared over n squared. E is the energy, that's what we're looking for. K is the Rydberg constant. Some textbooks, some professors will, instead of using K, will use R sub H. But this is a constant, it's always the same value. It's equal to 2.197 times 10 to the minus 18th joules. Z is the atomic number, and it's equal to the number of protons in the nucleus, which is also going to be equal to the number on the periodic table of whatever element you're talking about. So, for example, hydrogen has an atomic number of 1 proton in the nucleus. Helium has an atomic number of 2 with 2 protons in the nucleus. Lithium is 3, and so on. And N is our orbit. So, our question is asking us about hydrogen, and hydrogen has an atomic number of 1. So we're going to use 1 for this value, and the orbit that we are talking about is 3. So for this question, we just need to plug our 3 numbers into this equation. And our answer is negative 2.421 times 10 to the minus 19th joules. Problem 2. An electron in a hydrogen atom transitions from n equals 4 to n equals 2. Question A, is energy absorbed or emitted? Question B, what's the energy in joules? C, what's the wavelength in meters? And D, in what part of the electromagnetic spectrum do we find this radiation? So for question A, the energy is emitted because we are going from a higher energy level to a lower energy level. We are going from n equals 4 to n equals 2. Whenever it's higher to lower, it's emitted. Whenever it's lower to higher, we need to absorb energy. So question B, a lot of times what we care about isn't the energy level of any one specific orbit, but the transition or the difference between 2 energy levels, because that is equal to the energy of the photon that's absorbed or emitted. So what we care about here is the change in energy, delta E. Now, photon wavelengths and things along those lines are always going to be positive, so I'm taking the absolute value. This is going to be equal to the absolute value of the final energy level, EF, minus the initial energy level, EI. Now, the equation we used in that last problem, we can substitute that in here for EF and EI so that we don't have to use Rydberg constant and atomic number twice. And the equation that we come up with when we make that substitution is absolute value of change in energy is equal to the absolute value of negative k times z squared in parentheses 1 over final orbital squared minus 1 over initial orbital squared. And from here, we can plug in our values. So we have absolute value of negative Rydberg's constant times our atomic number for hydrogen is 1 squared times in parentheses 1 over our final orbital squared, 2 squared, minus 1 over our initial orbital squared, 4 squared. And this is equal to change in energy of 4.119 times 10 to the minus 19th joules. So question C was to find the wavelength in meters. This equation that we started with is equal to something else. It is equal to hc over lambda. H is Planck's constant, so it's always the same value, 6.626 times 10 to the minus 34th joules seconds. C is the speed of light in a vacuum, 2.99792 times 10 to the 8th meters per second. And lambda is our wavelength. So we're looking for the wavelength in meters. We need to rearrange our equation to solve for that. And from here, we can plug in some values. So wavelength is equal to h, which is Planck's constant, times c, which is speed of light, divided by our absolute value of the change in energy, which was our answer for the last question, part B. And when we plug all of this in, we get a result of 4.822 times 10 to the minus 7th meters. And a lot of times wavelengths are in units of nanometers. So if that's the case, you need a unit conversion using the metric prefix, and you would get 482.2 nanometers as your wavelength. Now, question D is, in what part of the electromagnetic spectrum does this lie? Well, you'd need to reference a chart, and you would see that it's in the visible region, and specifically it's a bluish green. But we still have a problem. This model and these equations only work for atoms and ions that only have one electron. That means it works for an uncharged hydrogen, for helium with a +1 charge, for lithium with a +2 charge. It does not work for multi-electron atoms or ions, or let alone anything with bonds. So we are not done figuring out the structure of the atom. We are also still missing a subatomic particle. Thanks for watching Chemistry in a Nutshell. And remember to bore into that like button.